Okay, so we are recording now and we are looking at the important concepts that are 100% going to be on the final exam. There are going to be questions from titrations, and in the titration we test whether you know the molarity of a substance. Molarity is moles per liter. So make sure that if the volume is given in milliliters, you convert it into liters. And we also look at the stoichiometric conversions. Do you understand when to balance the equation, the relationship in the moles? So this is what we test. And so you need to show during the working, you need to write the formulas, you need to write the units, you need to write the symbols and the formula of the substances and the steps, okay? Steps, all the details, even if you know them. Next is the limiting reactant problems. Here we test the relationship between the two reactants. How much of the product are you obtaining? So in this case, we test whether you understand the concept of molar mass. Can you calculate the molar mass of a substance? Can you convert grams to moles? Can you do the mole to mole ratio? These are the conversion ratios or conversion fractions that you get from the balanced equation. And then generally you can stop at the moles, but sometimes you need the grams. So can you convert the moles of a substance to a grams of substance? So all this. And the limiting reactant problems, in that the lowest amount of the product, that reactant becomes the limiting reactant, okay? Next, we test the percentage yield. Now, in the percentage yield, two things. One is the actual, the other is a theoretical. Generally, actual will be given to you. Actual will be given to you. But you need to calculate the theoretical. The question is not going to say calculate theoretically. Sometimes I put a little hint, but you know, the final exam, I would assume that you know that you need to calculate the theoretical yield. So once again, you will be given some amount of product. Percentage yield applies to the product. How much of the product? Now, theoretical yield is in theory. Keep this in mind that the actual yield should be smaller than the theoretical yield. So the answer should of the theoretical yield is just a little tricky, whether you know that you corrected it right or not. You can always check whether it's in larger amount or not. Theoretical should be larger. Okay. So one question from that. Then just the general stoichiometry, grams to mole, conversion moles to grams, calculation of the masses of the substances, especially the ones, the more complex ones, you know, where polyatomic ions are involved and there are brackets and so forth, okay? So in this case, it's okay to round up. Next is the gas stoichiometry. Gas stoichiometry, in this case, generally it applies to the situations where the gas is produced. So keep this in mind that what is it called? The single displacement reactions. Single displacement reactions. And then also the ones that relate to the activity series. Now, activity series are also, there is a table in your handout. So activity series, all the metals that are above hydrogen will release hydrogen gas. But the metals that are below hydrogen, copper, mercury, silver, platinum, and gold are below hydrogen in the activity series. So they cannot react with acid. They do not produce hydrogen gas. So again, amount of metal, amount of hydrogen gas that is released. So we're going to do some problems related to that. Then the gas laws are all algebraic conversion. Make sure here you're writing the units. Pay attention to the units. And if conversions are needed, you need to convert them. Make sure that the pressure. Generally, for your class, the millimeters of mercury and torr and atmosphere, you will see the conversions based on that. And then just make sure that the value of R, you're using the right one because it relates to the pressure. Okay. Temperature always converted into Kelvin. Volume always in liters. Okay. And the value of N. N is the number of moles. So these number of moles sometimes may not be given you. You will be given the grams. You need to convert to moles using the molar mass. So for your class, this is good enough. Next is how do you balance the reaction? Balancing reactions, like especially this combustion reactions. There is a trick to the combustion reaction. And in this combustion reaction, the trick is you balance carbon first, then you balance hydrogen, and lastly, you balance oxygen. Sometimes you have to multiply. So in the case of in the case of odd number of oxygens, you multiply the rest by 2. Okay, so there's the steps to that. We will look into this. Multiply by 2, the rest of it. Now, important thing we were talking about was the ionic and the net ionic equation. Here, these relate to the solubility rules. So you should know where they are in the table, or you should, if it's possible, memorize them, which is a good thing. Important thing here also in the ionic and net ionic, we also see whether you understand charges. Okay, whether you understand charges or not. Okay, whether can you balance the equation or not. So this is what we look at in all the details. Do you understand the concept of states? So always, if something is given to you in the form of solid, liquid, or gas, you are not going to ionize it. You only ionize those substances that are soluble in water. So those are the only ones you ionize. Now let's look at the concept of charges also. So we talked about these charges actually translate into charges, very important. These charges translate into the, what are these called? Like the tables, like the periodic table. Okay, coming from the periodic table. So we already talked about this. Now you guys are going to do this review with me. Group 1A, what would be the charge?
+1.
+1. And how many bonds can it make? And what are the valence electrons?
1.
And how many bonds can it make? 1. So 1A +1 charge, it gives electrons 1 valence electron, and it will make only 1 bond. Group 2A, charges? Come on, guys, quickly.
+2.
Valence electrons?
2.
Bonds?
2.
2. Group 3A?
+3.
+3 charge. Valence electrons?
2.
Valence electrons?
2.
For group 3A, how can it be 2?
Oh, sorry, 3. I forgot how to count.
Okay, how many bonds?
3.
Okay, 4A charge. It can be +4, it can be -4, and sometimes they don't give, because remember these plus and minus charges are coming by the transfer of electrons. So they can also make electrons, but they can also make bonds by sharing. Okay. So anyways, valence electrons, group 4A,
4.
4. Bonds,
4.
4. 5A, charge,
-3.
-3. Excellent. Valence electrons,
3.
okay.
5.
5. Very good. Excellent. And bonds, 3. Very good. So remember that octet rule. Octet rule is in the end, they are giving electrons. In this case, these guys are giving electrons. So they give electrons so that they can have what? A noble gas configuration. That is like the nearest noble gas, which is one period above. Okay. So they give electron to get that noble gas electronic configuration. Same story, this one, give or take to get that, and sometimes they share. So leave these guys in the middle because it's a mixture, metalloids also. So group 5A has 5 valence electron. It needs 3 more to get 8 electrons. That's one. 6A, charge?
-2.
-2, very good. Valence electrons?
6.
And bonds? 2, very good. 7A? 7A?
1.
-1. How many valence electrons? Don't get confused. 1 valence electron there. No, 7 valence electrons. They need only 1. So they can get 8 electrons in the last step. That is why they accept only 1 electron. They get -1 charge. Bond. How many bonds? 1. 8A. Charge?
0.
0. Valence electrons?
8.
8. And bond?
0.
0. But remember, there are some exceptions to the rule. And we discussed this because this is like not explicitly explained in the book, but then there are so many examples. So I already discussed the exceptions. So what are these exceptions? So why are they, first of all, let's look at it. What are cations? What are cations? Cations. Cations are they give electrons. So those ions that have a positive charge, plus charge, okay? Anions, they have a negative charge. So they have a negative charge, okay? So they can look like the nearest noble gas. Now, here is now another thing. So the exceptions are, so you just don't forget it, I'll quickly write this here. So the reason, first of all, why are they giving or taking electrons? So that they can follow the octet rule. And what is the octet rule? What is octet rule?
To have 8 valence electrons.
Say that again?
To have 8 valence electrons.
Yeah, the octet rule is to have the 8 valence electrons. That is why the metals, all the metals, they give electrons, okay, and they become cations. And the non-metals, they take electrons and they become anions. So next is the nearest noble gas configuration. So metals, when they give electrons, they electronic configuration similar to the noble gas, in one period above, okay? One period above. So for example, sodium has 11 electrons. When it loses one electron, it looks like what? Sodium has 11 electrons. When it gets rid of that one electron or gives away that one electron, it acquires a charge of sodium plus 1. But it looks like it has the electronic configuration of neon. Neon is 10. It is left with just 10 electrons. And that's one period above. Okay, so sodium is in third row and neon is in the second row. So that's the deal with most metals. Non-metals, they take electrons, they become anion. So in this case, they get the electronic configuration similar similar to the noble. So this should be noble gas. Sorry about that. Noble gas in same period. So let's look at this one now. You have oxygen. Oxygen is 6 electrons. It requires 2 more. Okay, it adds 2 more. So now what it has got? -2 charge. But sorry, oxygen is 8. Oxygen is 8, outermost is 6. Okay, so now it becomes oxygen 10. And that also looks like neon, second row. So this is this is oxygen 10, but it looks like neon. And this neon is a noble gas. And here oxygen and neon, both of them belong to the second period or second row. Okay, so they are very close to the noble gas, so it makes more sense for the non-metals, more feasible energetically for the non-metals to take electrons and look like the nearest noble gas, which is like very close in the same period. Okay, so that's one piece. Next is there are some exceptions to the rule, and those exceptions are, tell me, which atoms or which elements do not follow the octet rule. Let me put this in there. Exceptions. Yeah. Which ones do not follow the octet rule? So we have number 1 is hydrogen, helium, lithium, beryllium, and boron. So that's one thing, right? So these exceptions, the elements that do not follow, let's just put it a better way would be, these guys do not follow the octet rule. Okay, but if you look at the other guys, like for example, sulfur, the ones that defy means they can follow the octet rule. They defy the octet, they can defy the octet rule. Not all the time, but they can defy the octet rule. Which ones? They can defy the octet rule. Means, depends. If these elements of, if these atoms bond with a more electronegative atom. Okay, such as, like for example, in this case, sulfur. Sulfur, when it combines with, for example, in this case, with oxygen. Okay, like sulfur in sulfur dioxide and sulfur trioxide, right? So, or sulfur in H2S. So when sulfur is in H2S, it will make 2 bonds, but sulfur can make 2, 4, and 6 bonds. So it will make 4 and 6 bonds if it combines with oxygen or a more electronegative atom. Phosphorus can make 3 bonds, but it has the capability to make more bonds. So it will make 5 bonds also. Okay. Then you have chlorine, bromine, iodine. Okay. These guys can make 1 bond, but if they happen to combine it like chlorate, bromate, iodate, right? If that happens, then they can make 1, 3, 5, and 7 bonds also. So this piece is not explained in your book. Just make sure that you don't get confused when you're doing the Lewis structures. That's where it comes. This information is important. Anyways, so look at the noble gases. Noble gases are helium, neon, argon, krypton, xenon, and radon. So fine, they are all going to make 0 bond, but xenon can make 2, 4, and 6 bonds also if it combines with a more electronegative atom. For example, fluorine. Xenon can combine with fluorine, xenon can combine with oxygen. So those have been known actually. It's all about reaction conditions, okay? So keep these things in mind. And these are the ones. And then now comes the, so know that 10 is the Lewis structures. So based on this, I'll just follow this Lewis structure. Lewis structure. Now, I've noticed that students are so like in a rush to fill the octet of the atoms that they just start doing it right from the middle. No, no. Always choose the central atom. So in the Lewis structure, how do you choose the central atom? So first is the total valence electrons. Always do that. And there can be a question based on that. Okay, next is central atom. Which one again?
The one that makes the most bonds.
Very good. So central atom, not necessarily the one with the lower electronegativity, not that, but the one that can make the maximum number of bonds. Okay, so that's going to be the central atom. So that's one piece. You connect the central atom with the outer atoms, fill the octet of the outer atoms, and then do the rearrangement. So the kind of question that we can ask here is whether resonance. Do you understand the concept of resonance? What is the concept of resonance, guys? The students who are online also can respond through the chat. Okay, guys? So I'm asking resonance. What is the concept of resonance? Yes? Don't know? Resonance, where the double bond and the charges they kind of move around, shift in a molecule. And so for that, there are going to be multiple Lewis structures. Okay, multiple Lewis structures. Because you're rotating the double bond. Okay, so we will look at that. And now comes the, with that, you should know how to identify the shapes of the molecule. You should know how to identify the polarity of the molecules. So for the shapes and the polarity, right? I mean, I'm not expecting you should memorize everything, but for the polarity, what do you need for the polarity? What do you need for the polarity? Very important thing that you need. What is that? Say that again. Polar, okay, polar bonds, but how do you determine that?
Sharing.
How do you determine polarity? Something. Electronegativity. Very good. So for the polarity, you need to know the information about the electronegativity. So here's the thing, little cheat sheet or something that you learned in your previous lectures was, or in your previous chapters was the trends in the periodic table. As you move left to right in a periodic table, the electronegativity increases and the electron affinity also increases. As you go top down, so these are the trends in the periodic table. That's something you need to know again from top to bottom. As you go down from top down, so let me put this here, top to bottom. What happens to the electronegativity? Increase or decrease? Decrease, yeah. So the electronegativity goes down and the electron affinity also goes down. So you can be asked questions like compare, which one is more electronegative, which one is less electronegative. That's one piece. But when you look at the polarity, this is, another thing. Just, what is electronegativity? Define electronegativity. What does it mean? What's the meaning of electronegativity? How do you define electronegativity? Very good. How strongly the electrons are pulled. So pull of the electrons or attraction for electrons, pull of electrons. And that has been measured, right? On a scale from 0 to 4. So that's one thing. So that pull determines the hot and the cold centers in a molecule. Now comes the question that if you are given a molecule, okay, which has got polar bonds, right? Polar bonds. So if the pull of the electrons, or if the polar bonds are the same polar bonds, or on both the sides, if the pull is the same on both the sides, then it cancels out. Then the overall molecule becomes non-polar. Okay, the net polarity, the sum total of that pull from all the sides, it cancels out. So that's why, even though there are polar bonds in a molecule, equally distributed polar bonds, but overall the molecule would be non-polar. Like for example, here you have carbon. Carbon with double bond here and double bond here. So carbon-oxygen bond is a polar bond. So this is a polar bond and this guy is also a polar bond. Now two polar bonds on both the sides, but opposite directions. So this oxygen is pulling the electron clouds towards the side. This one is also pulling. So the effect cancels out. So even though the bonds are polar, the actual molecule is non-polar. Have you ever touched a dry ice? Have you touched a dry ice? How does it feel? Yeah, see, you can tell whether something is a polar or something is non-polar. Non-polar will be like softer, would be like grease or like oil, like cream, that kind of feel you will get. So if you touch a dry ice, it's very cold, obviously, but you can still touch and kind of get a feel for it. It's not sharp. But water, comparatively, you put the water in your hand, that feeling is different. You take milk and you pour milk in your hand. You feel that softness, right? But you take water and put water in your hand, you can clearly feel like it's water. And that feeling of water. because water is polar. Anything that is polar will have that sharp tingling sensation, or that feel is different. Anyway, so that's carbon dioxide. So overall, this molecule is non-polar. So keep that in mind. Don't forget that, okay? Non-polar molecule. Okay, now shapes. So for the shapes, again, I'm not expecting you that you remember the shapes, but what are you going to do with the shapes? You are going to look at, for your course, molecular shapes. Molecular. So molecular shapes are from outside. Molecular shapes are like how the molecule looks from outside. That is why you guys do the molecular modeling. So from outside look of the molecule. Okay. I mean, obviously you can't see the molecules, but that's, one piece. On the other hand, electron geometry. On the table, you will see electron geometry also. Now mark this, don't ask me on the exam. I'm not going to tell you this. I'm just telling this again. Electron geometry is inside. And where do you see this information? How the molecule looks from inside, the inside look. Like the mansion looking from outside versus you go inside the mansion and start looking at the different rooms and the kitchen and so forth. So that's what is it. So anyways, so for the shapes and this, where will you look? You guys have a table, right? You guys have a table in your handout. You can check that, okay? So the trick here is to get the right shape and the right polarity is draw the correct Lewis structure. If the Lewis structure is wrong, everything goes wrong. So correct Lewis structure only, okay guys? All right, now we have, okay, so we did that, 11. And with that, the question, that's a kind of interesting question, the intermolecular forces. What are the intermolecular forces? Intermolecular forces. Yes? Yeah, so in intermolecular forces, there are dipole, sorry, low battery, hold on. Forces, dipole. So what are dipole? Dipole are when a molecule has two, like there are basically polar molecules. So you should be able to look at a molecule and look at a polarity in a molecule. So polar molecules will have a dipole. Okay. Next is the London dispersion. Now, okay. London dispersion is just a spread of the electron cloud. Okay. Spread of electron cloud. So London dispersion, all the molecules have it. Spread of electron cloud. All the molecules will have it. All of them have it. So, just don't even worry about all molecules. And yes, dispersion is just if the question is just dispersion alone is hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, like these will have dispersion forces. Then comes the hydrogen bonding. So what is a hydrogen bond? Hydrogen bonding actually is present, or is the rest of the molecule, we don't care. As far as there is oxygen and hydrogen attached, like on one side. Again, R is the rest of the molecule. As far as there is nitrogen and hydrogen attached, and then this is another R. Okay, or between fluorine and hydrogen. So fluorine attached to hydrogen. Okay, so here we see this hydrogen will participate in hydrogen bonding, not the hydrogen that is attached to chlorine, bromine, or carbons or anything else. Okay, now here, oxygen being more electronegative will have a delta negative charge. Hydrogen being less electronegative, delta positive. Oxygen pulls the electron clouds towards itself, but oxygen also has these lone pairs. This nitrogen has a lone pair. Nitrogen, more electronegative, pulls the electron clouds towards itself, so it gets a delta negative charge. Hydrogen gets a delta positive charge. Here, fluorine. Fluorine is very highly electronegative. The most electronegative element is fluorine. So fluorine will have a delta negative charge. This hydrogen is delta positive. So yes, these are all polar bonds, but keep this in mind that hydrogen bond occurs between the oxygen or nitrogen or fluorine of neighboring atoms or neighboring molecules rather, neighboring molecules with hydrogens of neighboring molecules, I don't know, of another molecule. Okay, so in this case, you will see that in this case, like for example, you have a molecule such as this, CH3, and here CH2, and CHOH, and H. So in this molecule, this whole segment right here is nonpolar. These hydrogens are very strongly bonded to carbon. They're never going to be released. The only thing that is polar is this guy. Let's just make it a different color here. Is this site is very polar. Okay. In this case, hydrogen delta positive, and oxygen delta negative. So this molecule is a polar molecule. So if this molecule will have, yes, London dispersion forces, this molecule also has the dipole because one side is non-polar. All these carbon hydrogen bonds are non-polar. Okay, always carbon hydrogens are non-polar. And the OH side always, or NH, or wherever you see the electronegative atom, that side is going to bring in some polarity in the molecule. So this is the polar end, one side is a non-polar end. Just the presence of the two different ends bring a dipole, and there is hydrogen bonding in this one. So you can be asked if these are the three intermolecular forces. More the intermolecular forces there are, more intermolecular forces, higher the boiling point is. Okay. So if you have hydrogen bonding, because of the OH group, boiling point is going to be very high, like water. Okay, so this end participates in hydrogen bonding. And how does that happen? Now let's just do this here. I'm going to just put rest of the molecule is R, which does not even participate, but you have this oxygen, this hydrogen, these two bonds right here, and let's do one hydrogen, oxygen, and R. Okay. So what is happening here? In this case, this oxygen lends its lone pairs to this hydrogen, and the bond is not broken. Like in the acid, you see the bond is broken, and here this is negative oxygen, negative. This guy is delta positive. This guy delta positive, and this oxygen lends its lone pairs to this hydrogen. So this very weak network, it is a very small, like a very weak bond. So this weak network of attraction, right? So intermolecular forces, which is called the hydrogen bond. So this is the hydrogen bond. So don't get confused between the hydrogen bond is like hydrogen, two hydrogens connected. Okay, guys. So that piece. All right. So we did that, and then next is you should know the electronic configuration. Okay, just make sure that electronic configuration, and in the electronic configuration, you should know how to draw the orbital diagrams. Orbital diagrams and orbital diagrams, and then what is the other one? Valence electrons and d block. Okay, so let's look at this guy, the electronic configuration of iron. Electronic configuration of, oh, this is, sorry about that. Okay, this is okay, iron. Okay. Iron is for iron. Iron has 26 electrons, and here 1s2, 2s2, 2p6, 3s2, 3p6. Now remember that after 3p6 comes 4s2, and then comes the 3d. Now here's a cheat sheet for the d block. If they, whatever this number is, that number is here. That goes on the d. Okay. Okay, guys. So remember that the S, the 4 comes before D. Okay, clear? 4 comes before D. Now, if we are saying draw the orbital diagrams, draw orbital diagrams. So which are the valence electrons? Valence electrons are the last electrons. So which ones are the last electrons in this case? Everyone? Yes, the students who are in the joining the Zoom meeting. Which ones are the last electrons? Is it the 4s or 3d? Come on. Yes. 4s. Very good. 4s. So sorry about that. Okay. From the D block element, and just make sure that 4s has to be written before the 3d. Fill that one up and then just do it. So if I ask you a question, so let's do this. Now, if I give you a question for Fe plus 2, okay, and Fe plus 3, Fe plus 2 and Fe plus 3, sorry, write the electronic configuration. So do it, Fe plus 2 and Fe plus 3. So, and if I say, write it in the condensed form, condensed is what? The inner core is of the nearest noble gas. So, the nearest noble gases are like 2 plus 2, 4 plus 6, 10. And then you can go further, plus 2 plus 6 is 18. So you see here, the inner core is of 18. This inner core is 18, right? And 18 electrons look like, which nearest noble gas? Which one? Argon. Remember always, to look at the periodic table if you are not familiar, but argon has 18. So you can write down the inner core 18. So this question can also be asked where you are being asked to write the condensed form. So argon is taking care of 18 electrons, and then you just write down here 4s2 and 3d6. And for now, tell me, where should I take the 2 electrons out from? 4s2 or 3d6? Yeah, 4s2 or 3d6? Which is the last? It's always the last. It's always from the valence. So it is 4s0 and 3d6 will remain as it is. Okay, so the electrons will leave from, so the -2 electrons are from the 4s2. Okay, now 4s3 will be where? From where? 4s3. So you have 4s2 and 3d6. So from where?
No.
-3 electrons from where? And then what? Why is that so?
Because 4s2 only has 2 electrons. We have to take the third from 3d6.
Yeah, and 3D and 1 is coming here, so it becomes 3D. Fine. So keep this in mind, that rule. What is that rule? Hund's rule. Half filled and fulfilled orbitals are more stable. Half filled and fulfilled orbitals are more stable. So iron with its +2 state, you find more, like FeCl3, it's more prevalent. Okay. So anyway, so half filled and fulfilled orbitals are more stable. Stable means less reactive, commonly found. Okay, and another type of electronic configuration that can be asked is, let us say copper 29. And you should do for copper, copper +1 and copper +2. Okay. Yes. Same story. Inner core argon, that's 18 electrons. Then you have 4s2 and 3d. 3d what? Remember I told you this little cheat sheet here. 3d? No, not 6. 3d? Matthew?
9.
9. Good. 9. Very good. Remember that last number and this number. This 6 and this 6. Thank you. Okay. So now, anyways, so copper +1 would look like what? Argon, inner core, this remains unaffected. So what should I do next? Copper +1. 4s1. 4s1 and 3d9. So it depends on the reaction conditions and the temperature conditions, all those things. So copper +1, quickly the electron goes from there. That can also happen, or another, if we just move one electron, yeah, another thing can also be 4s0 and 3d9. That is also a possibility. 3d10, yeah, 3d10. So internally, that electron has jumped. Remember 4s2, one electron can jump from 4s2 to 3d9 to make it 3d10. So in that case, then this thing will become, let's do it this way, argon 18 and 4s1 and 3d10. This is more stable form. This is more stable. You get that? This S2 has, one electron has jumped from here and gone to the D. And when you will study this in hybridization, this happens. Okay, so then you get 4s1 and 3d10. So this is fulfilled orbital, more stable. Okay, and now when you lose electrons, so this guy is gone, or in other words, this one is gone and this is left. Very stable. Okay, so argon 18, and now next is copper +2. What do we do here? So the electrons do not get time to jump. So here it would be 4s0 and 3d9. That remains, like, quickly the 2 electrons have gone from 4s0. Okay, you got it? So that type can come. Now, on the other hand, if I give you S -2, write the electronic configuration of sulfide. So how would you write that? Sulfur is, what is sulfur? 16, right? So 1s2, 2s2, and 2p6, 3s2 and 3p, what? 10, 11, 12, 13, 14, 15, 16, 4, 3p4, okay? Now, 3p4, so if I ask you, no, so this is just for sulfur, sorry, this is just by the sulfur. So if the electronic, the orbital, so first is the condensed. The condensed would be, or the noble gas configuration. Noble gas configuration, okay, is what? The inner core is 10 electrons. So that 10 electrons belong like neon. So neon 10, and then 3s2 and 3p4. All right. Now we have the orbital diagram. Orbital diagram. So orbital diagram is only for the outermost, the valence. How many electrons are there in the valence shell? Sulfur. How many electrons in the valence shell? 6. Remember, it's in group 6 anyway, so these are the 6. So these 6 electrons are the valence electrons. So 6 valence electrons, you put them in the noble gas. So in the orbital diagram. So P, how many orbitals are there in P? How many orbitals in P? 3. Good. Okay, so we have here 3s2 and 3p4 is 1, 2, 3, and so first always singly occupy and then pair. First, singly occupy, then pair. Okay, so here we will see the in this case, yeah, so this is the 3s2 and this is 3p4. So how many electrons are unpaired? 2. So 2 unpaired electrons need to be paired. That is why S minus means 2, S minus 2 means 2 more electrons. So this S minus 2 comes when sulfur acquires 2 electrons. So here is a sulfur plus 2 more electrons becomes S minus 2. This also need to look at it, the Lewis structure. Sulfur has 6 electrons, 1, 2, 3, 4, 5, 6. Plus, when it acquires the 2 electrons, the sulfide becomes 1, 2, 3, 4, 5, 6, 7, 8. So 6 electrons plus 2 more electrons from outside. It has got now 8 electrons. Octet is met. But it will have -2 minus charge or -2 charge. Okay. So in that case, where are you going to put? So here is your sulfur -2, neon, the way it is. And then comes the 3s2 and 3p4. 3p6, sorry. So here 3s2 and 3p6. And all of them get paired. So always first singly occupy the degenerate orbitals, which is the p orbitals. All right. Okay, so that's for the sulfide, same thing for the oxygen, right? So these are the orbital diagrams condensed. We talked about the d orbitals. Okay, now another question, just for your knowledge, based on this is that now S, P, D, and F. S subshell, how many orbitals? Yeah, one orbital. So orbitals and sometimes the distance get confused. P subshell, how many orbitals? How many orbitals in P? 3. D, how many orbitals? 5. And F, how many orbitals? 7. Excellent. Don't forget that. Now, how many electrons in S orbital maximum? How many it can hold? 2. 2 electrons. P can hold a maximum of how many? 6. Good. And then D maximum? 10, excellent. And F, 14. Good. Okay. So that's what we have. The rest is obviously, the nomenclature and all that you should know. So, review the nomenclature worksheet. That I can, nomenclature, writing the formula. So this is, nomenclature is actually a very important part of your student learning outcome also. Okay, so make sure that you review the worksheet. Review the worksheet. All right, now, let's look at some of the problems from the book. And I really want you guys to do well. So I'll take some more time here, like maybe I think another half an hour, 45 minutes, we should be able to do this. Finish this specific problem. Okay, after that, you guys have a lab checkout and then we're done. Okay, so, sorry, where is my, give me 1 second. Okay, so we are looking at the problem from the book, and that is the problem. Give me 1 second. Okay, here. This is the titration problem. And like I said, some of these problems are going to be not the exact same ones, but similar. Okay, so let's just do a few so that you guys get a hang of it. Okay, so number 1, titration is where you determine the molarity or the volume, generally the molarity of the other substance, generally acid-base titrations. Okay, so what is the molarity of H2SO4 solution? Let's do this one, 11.63, 11.63. Okay, here. If 38.2 milliliters of KOH, so you are given KOH and you are given the volume of KOH, which is 38.2 milliliters, okay, of KOH of 0.163 molar. So the molarity is 0.163 m. Is required to titrate 25 ml of H2SO4. So write down that H2SO4 is, the volume given is 25.0 milliliters. And the question is, what is the molarity of H2SO4 solution? So find the molarity of that. Okay, so you write that down and you make sure that you write the balanced equation. So here's your problem. So always write down first the balanced equation. So in this case, remember, we talked about the outer, inner. So here's the outer metal. Metal is going to combine with the non-metal or the polyatomic ions of the other atoms, of the other molecules. And the non-metal or the polyatomic ion of one reactant is going to combine with this one. So what do we see here? We see K. What should be the formula, guys? When potassium combines with sulfate, what should be the formula?
B1 over M1?
No, no, right here, the product. Remember, outer, inner. K.
SO4.
Okay, K, SO4, are you sure? Are you sure it's K, SO4?
Yeah.
0. What is the charge on sulfate? Do you recognize sulfate? Polyatomic ion. SO4 minus 2. Remember, I asked you guys to memorize? Remember that, guys? So you don't forget that. And non-metals also, see guys? And metals. So at least you should know their symbols of like the important ones. Okay? All right? And in case you're confused, you have the hand up. You can always refer there. So potassium, what is the charge on potassium? Yes, charge on potassium. 1, +1. Why is it +1?
This is the first.
Group 1A, very good. So you see this number comes here and this goes here. So So that is why this becomes K2SO4. I'll do more some practice with you after the 15 minutes. So here is this H2O. H2O. Is this balanced? Balance it. So we put 2 here. Potassium is not balanced, right? It's K2. So here it's K. So 2 here. So this gives you what? 2 potassiums, 2 oxygens, 2 hydrogens. So there are actually 4 hydrogens. So 2 here. So 4 hydrogens, 2 oxygens, and sulfate. So, just for balancing purposes, it's okay to keep the polyatomic ions intact. So you can see there's 1 sulfate here. Okay. So now, all right. So here in this case, you are given the volume and the molarity of the base. And you know the volume of the acid, but you need to find the molarity of the acid. And the process, we already discussed that. But what is the first step? Number 1, always. Whenever it's a molarity, the milliliters need to be converted to liters. Always do that. So 38.2 milliliters times 1 liter over 1000 milliliter becomes what? It's 0.0382 liters. Same story with the other one. 25.0 milliliters times 1 liter over 1000 milliliters is equal to 0.025 liters. Okay, so that's, just get it out of the way. Next, what are you going to do? Yes. What will you do, guys? You know the volume, you know the molarity of KOH. What can you find? Moles. Very good. So for this, the important step is find the moles of the base or the acid, whatever entity is given you. So in this case, find the moles of the base, and that base given is KOH. Okay, how would you find that? What is the formula for that? Moles is equal to molarity times volume in liters. So the moles, so it's very important, guys. Please learn to write technical writing. That's something you guys have done. Many of you have done an excellent job, but many of you still need to pay attention to detail. So moles of KOH. So this is the way you can write. Okay. This is how we use a very symbolic language. Okay. Molarity is 0.163 m times the volume in liters is 0.0382 liters. Okay. So do the multiplication. Multiply. Okay. What do you guys say? 0.163 times 0.0382 is equal to
0.0062.
Very good. 0062 and 2. Okay. So because remember, this is the 3 significant figures, so 3 significant figures. Do that, okay? But do not round up. So anyway, so these are the moles of KOH. Then what will you do next? What's the next thing? The students who are joined can also, participate through chats. Okay, next is find the moles of acid. Okay, on the acid, and in this case it is H2SO4. Okay, H2SO4. So how would you do that? You take the moles of the base, times the conversion factor or the mole to mole base. So here you have the moles of the acid from the balanced equation over the moles of the base. And this is going to give you the moles of the acid. So let's do this piece right here comes from the balanced equation. Okay. So we have 0.00622 moles of base times from the balanced equation, we see that 1 mole of KOH reacts with 2 moles of KOH react with 1 mole of H2SO4. So 1 mole of H2SO4 over 2 moles of KOH. Okay, so 0.00622 now divide by 2 and you get 0.00311 moles of the acid H2SO4. Okay, guys? 4. Now you take the moles of H2SO4. We need to find the molarity, right? So you have what is the formula for molarity? What is the formula for molarity? Molarity is moles over the volume in liters. So we know the moles of in this case, the molarity of H2SO4 is 0.00311 moles of H2SO4. Divide that by the volume in liters, which was 0.025. 0.025 liters. Okay, divide that by 0.025 and you get 0.124 m. That is a unit for molarity and that is for H2SO4. Okay, so if you follow these steps, you won't go wrong. Clear? Okay, let's look at the next question on limiting reactant. Okay, so here we see the problem from your on the acid base, the direction of the equilibrium. Direction of equilibrium, and this is also called the proton transfer reaction. So, okay, so you are given this problem, NH4 with a positive charge, okay, and this is aqueous reacting with H2O liquid, okay, and this at the equilibrium gives you NH3 aqueous, okay, and it gives you the H3O plus charge aqueous, okay. Now, in this case, you see, obviously, if you have OH, that is always going to be as base. So keep that in a little cute sheet here. Sheet. That wherever you have OH minus, that is always going to be a strong base. So in this case, we do not know that, you know, we say we do not have the OH, so we don't know which one is the base, where is a strong base. That's one thing. Second thing is that remember that H2O can be an acid and H2O can be a base. So don't rely on this thing, on the oxygen. Don't start with that. So what is the process here? You are first going to identify, always first identify acid and base. First identify the acid and base. So remember that the water is can be both, so you can't start with water. Okay. Now, next thing is, what do we know about ammonia? There's something you should know just about ammonia. That's another thing about ammonia. That is just knowledge from the knowledge. Ammonia is always a weak base. Okay. So this is from your knowledge. If you have OH present somewhere, that's going to make something a strong base, then wherever ammonia itself is a very weak base. Okay, so this is again from your common knowledge. So once you identify that, then just keep this in mind that the other guy will be an acid. Okay, so identify the acid and base. So here you have NH3 and H3O. And always remember that another thing, more hydrogen in front. That is in front, always that's going to be an acid. Okay, so these are the weight, like these are the pointers that point you to know in one direction. You're trying to identify the acid and base. So you look at this. This is more hydrogen than water, right? More hydrogen than H2O. So obviously this guy is acting as an acid. And ammonia is a weak base. Ammonia is a base. But I mean, actually, it is a weak base, but everything is relative and comparative. So ammonia is basic. Basic. Okay, basic means weakness. Anyway, so you identify that. Next is, now we are left with NH4 and we have H2O. Okay, so here keep that in mind that we cannot start with water because of the dual nature of water. So obviously we have to start from here. Start here. Okay, identify these two bytes. Next, what's the next thing? What's the next step? Yes. Next step is?
See which is stronger or not.
Say that again.
Check which is stronger than the other.
No, before that. There's one step before that. Every acid has a very good. Every acid has a conjugate base, and every base has a conjugate acid. So let's put it here that every base has a conjugate acid. Okay. Now, acid. So we identified that NH3 is a base. So what is the conjugate acid of NH3? NH4 plus. Remember, it's always one hydrogen ion added. So this is NH4 plus. And in this case, we have H3O plus as an acid. So what is the conjugate base? Conjugate base is less hydrogen ion. So minus one hydrogen ion, and that is H2O. So that, you see this question tests your knowledge of, your understanding of conjugate acid base pair. So here I'm going to use this pointers are for knowledge. You should have this knowledge at least to start with. Okay. Now after that, what do you do? What do you do after that, guys? You compare. What are you going to compare? Now this is where many people make mistake. You compare what? An acid to a very good. An acid versus a conjugate acid, and you're going to look at whether it's strong or weak. So conjugate versus acid versus its conjugate acid, and a base versus the conjugate base. All right. So now you compare H3O plus with NH4 plus, and you will have NH3 with H2O, and figure out which side is the stronger and weaker. So when you do the comparison, where do you look? And that table is in your handout, and it's 11.3. So let's look at this table. So here we have ammonia and water. So ammonia is acting as a base and water is a conjugate base. So this is the water you will compare. Okay. So some students made a mistake and they looked at this water. So don't do that. So if your water is on the basic side, base to a base. So here's the ammonia and here's water. So which one is a stronger, ammonia or water? Because you're going, stronger this side. Very good. So you have the ammonia is stronger. Ammonia is stronger and water is weaker. Okay. And on the other hand, now hydronium ion to ammonium ion. So here's the hydronium ion on the top right here, and the ammonium ion is NH4 right here. NH4. So which one is stronger, the hydronium ion or the ammonium ion? Yes? Hydronium. See, remember, this is going up, it's moving up, it's increasing here. So hydronium is stronger. So let's go back and hydronium is stronger and this is weaker. Okay, now you just go back and put it, and then what is the rule? Yes, guys? What is the rule? Yeah, what is the rule?
It's the stronger side.
Yeah, it moves actually from stronger to the weaker side. So here we are trying to find out which side. So here you just identified it, and this is the, let me write this down, NH3, and you have H3O plus. So we have ammonia is stronger, and hydrogen ion is stronger, and then ammonium ion is coming out as weaker, and water is weaker too. So the rule is that the flow of the hydrogen ion is from wherever the stronger side is. So stronger to the weaker side, and the flow, so that's the hydrogen ion flow. So the reaction is moving actually backwards in this case. Okay. All right, guys. So these type of questions, we test like, other things also for the comparative understanding of acid base. Okay, next question, let's look at, I didn't cover that Le Chatelier's principle also. You guys, I think, are okay with the Le Chatelier's principle, but let me put this here.
Wait, so I have a question. So basically, the reactant is more in favor because on the other side it's more stronger, and so I need to like stable it up. That makes sense.
Wherever the stronger side is, the stronger means it has got more hydrogen ions that side.
Yeah.
So it gives away the hydrogen ions to the weaker side.
Right.
That's how they balance.
Okay, I got
you. And then the 16 is the equilibrium. Say that again. Okay, yeah. Yeah, so which one are you saying again? I mean, I can only cover important and very important pieces. You still have to go back and review. Yeah, go ahead. Which one did you say? Yeah.
Fourth step. Oh, sorry.
I didn't get that. Say it again loudly.
Can you show the fourth step? Yeah, like the fourth step on the previous question. Example.
Oh, this problem right here?
The last step, sorry.
The last step here?
Yeah, that's right. That's it.
Oh, the fourth step. I see.
Yeah.
Okay. Thank you. All right. Okay, so this one was the difficult one. Let's get another one. Yeah, guys, gas laws, please make sure you write the formula for all the gas laws. Many people forgot to write Dalton's gas law. I mean, it's a very simple law. P total is equal to P1 plus P2 P3. And I saw that many people did the conversion of, ATM to millimeters of mercury, torr to ATM, those things. So that is also good. So you make the same, but you forgot to write the formula. Dalton, uncle is not going to like it. So Dalton's law is P total is equal to P1, P2, and P3. So make sure that you write that formula, okay? Okay, then so any question from your test that you guys need?
How many questions?
I don't know. I didn't make the test yet, but there's certainly 25 to 30 questions. Okay, so but you have to do all the work. Okay, let's look at the other problems here. to turn on the recording. So anyway, so we are looking at this problem on limiting reactant. The question is not stating directly find the limiting reactant, but the question is asking how much of the product is obtained when a certain amount of the two reactants are used. So in this case, we are looking at H2S. How much can you produce when you use 15 grams of Al2S3 and 10 grams of H2O? So here we are looking at directly the relationship of aluminum sulfide with H2S and water and H2S. The amount of product that you're going to produce is going to depend upon the limiting reactant. So directly the question is not going to ask, but it's implied. So anyway, the first step is find the molar mass of aluminum sulfide. So what is the Al2S3 is made up of 2 aluminum and 3 sulfur. So what is the molar mass of aluminum? Yes? Molar mass of aluminum? Molar mass of aluminum, yes? 27. Okay, and sulfur? 30? Okay, so 32 times 3 plus 27 times 2, what do you get? Say that again? How much? 150?
196.
The 150?
Yes, 150.
Grams per mole, write that unit. Okay, H2O, there are 2 hydrogens plus 1 of oxygen. And you have 2 times 1 plus 1 times oxygen, it's okay to use 16. So this becomes what? 18 grams per mole. And H2S, so 2 of hydrogens plus 1 of sulfur, and that is 2 times 1 plus 1 times 32. So this becomes 34 grams per mole. Very good. Now, so that just put this on one side. Now divide your paper or just do it in 2 steps. So let's look at it first one of Al2S3 and how much of the H2S can you produce from here? When you use 15 grams, right? So 15, always write down. See, pay attention as I'm showing you. 15 grams Al2S3 multiply by 1 mole of Al2S3, divide that by the molar mass, which is 150 grams of Al2S3. So what is this first step? What is the first step doing? Grams per mole. Very good. So this first step is either you can break it up into steps or you can just do it in one line. But anyways, it still means the same. So you have taken the grams of Al2S3 and you're converting it into moles using the molar mass of aluminum sulfide. Okay. Now we move to the next step. What is the next step here? Next step, everything is in front of you. Mole to mole ratio. So how many moles of Al2S3? 1 mole of Al2S3. Very good. And what should I write on top? 3. Very good. 3 moles of H2S. Excellent. Okay. So this piece you always get from the balanced equation. So it's very important to check the balancing of the equation. Okay, so this is the balanced equation. All right, now multiply. What's the last step? I mean, you can stop here, but the question is asking how many grams, so we have to move forward here. So what do you write in the last step?
1 mole of H2S.
1 mole of H2S, very good, at the bottom, because you want to cancel out the moles of H2S and convert it into the grams of H2S. And that is, what should I write on top?
34 grams per mole.
34 grams per mole, very good. So 34 grams of H2S. Now, this last piece is converting basically the moles of H2S to grams of H2S. All right, so grams of Al2S3, grams of Al2S3 cancel out, moles of Al2S3 and moles of Al2S3 cancel out, moles of H2S and moles of H2S. So the only unit left is that of grams. All right. Next is, what do you do next? You take 15.0 times 1 times 3 times 34, divide that by 150 times 1 times 1. So what do you get here? Yeah. Does it mean 10.2 grams of H2S? Very good. Let's look at the next one, which was the H2O and H2S. Okay. Okay, H2S is, we have 10 grams, right? 10 grams. Yeah. So 10 grams of H2O, same thing, convert that to mole. So 1 mole of H2O over what? Yeah, 18. Very good. 18 grams of H2O. What should I do next? Mole to mole ratio. So 3 moles of H2S, and this comes from the balanced equation, 3 moles of H2S over 6 moles of H2O. So it's okay to write the way I'm writing here for the sake of space. After that, 1 mole of H2S gives you 34 grams of H2S. And next is same thing. You have grams of water cancelling out, moles of water cancels out, moles of H2S cancel out. So now you're left with 10.0 times 1 times 3 times 34. Divide that by 18 times 6 times 1. What do you get here? Yeah. You guys, what do you get here?
9.44.
9.44.
Yeah.
44 grams of H2S. So how much will you produce? How much will you produce? 9.44. So the lowest amount, so always so H2S 9.44 can be produced because, and then which is the limiting reactant?
H2O. H2O.
Yeah, H2O is acting as the limiting reactant. Okay, guys. So if you understand this arrangement, then I think many of you are okay with that. Some of you might need some practice, but just practice it on your own, okay? All right. So now you guys are telling me that you need to learn the net ionic equation and ionic equation, okay? So let's look at it from the books, examples. Okay. Okay, so here we are looking at these problems from this problem chapter 9, and these are the identifying the products, balancing the equations, identifying the solubility, and then ionizing, and then finding the net ionic solution. So first of all, it's very important you recognize the metals, the non-metals, polyatomic ions, charges, and you should know how to access the solubility table so that you can identify the liquid solubility or aqueous solubility, sorry. Okay, so now sodium, when it combines with nitrate, and silver, when it combines with phosphate, it produces the substances, and we're writing the right formula so that we don't make mistakes. So this is how we do it. Sodium, the charge on sodium is +1 because it belongs to group 1A. Phosphate, standard, it doesn't change, always it's -3. Silver is connected to one nitrate ion. So that means the charge on silver is, nitrate is -1, the charge on silver is +1. Got it, everyone? Okay, now you just put these together. Here sodium and nitrate combined, here silver and phosphate combined. So now let's put them. So here you have sodium +1 charge and nitrate. Then sodium has +1 charge and nitrate has -1 charge. So what happens when they crisscross? This guy comes here, this number 1. This number 1 comes here, but for 1 and 1 we don't, right? So what is the formula now? NaNO3. Okay. Now silver with +1 charge and phosphate -3 charge. So here is the silver with +1 charge, and here is the phosphate -3 charge. So now you combine this 3 over here and this over here, crisscross. So what does the formula become? Yes, Ag3PO4, phosphate, PO4. And for 1 we don't know. Got it, everyone? Now, balancing. So let me write this down again. Na3PO4 plus AgNO3 gives you NaNO3 plus Ag3PO4. Balancing. So how many silvers do you see? I mean, some things by this time, you kind of get it. So 3 silvers here, 1 silver here. Obviously not balanced. So you put 3 here, right? So now you have 3 nitrates. Remember this 3 applies to silver. This 3 applies to nitrate also. Okay. So we have 3 nitrates. Here, how many sodiums do you have? This 3 applies to sodium alone. This phosphate is just by itself, one big thing by itself. Nitrate is just one big thing by itself. Here you have 1 nitrate, but 3 nitrates on this side. So if you put 3 here, this 3 applies to sodium and balances the sodium, makes nitrates 3. Silvers are 3 and there's only 1 phosphate. So 1 phosphate, PO4, and here you have 1 phosphate. You have 3 Ag, you have 3 Ag here. You have 3 NO3, you have 3 NO3, you have 3 sodium, and you have 3 sodium. Balance. Now, interesting thing here is that during balancing, it is okay to not put charges. Okay? So this is just like a little thing on the side you're doing small working. But that's your balanced equation. You have already made the ionic equation now. So why are you scared? Just put the charges now. I mean, that part somehow the students get really confused here. Now just put the charges. So you are able to write the right formula. All you need to do is just the charges now. So how many sodiums are there? Oh, before charges, we need to look at the solubility also. Sorry, solubility. So, okay guys, so here you have Na3PO4, soluble or insoluble? Na3PO4, is it soluble or insoluble? Remember, anytime group 1A attaches to anything, soluble. Okay, soluble. So when it's soluble, how do you write soluble? S. No. S is solid. Don't get confused. Yeah, aqueous. Okay, next is silver nitrate. So 3 AgNO3. Now tell me, AgNO3, soluble or insoluble? Nitrates. Anytime nitrates attaches to anything, soluble. very rich in electron, nitrate. So aqueous, soluble. Okay. I mean, silver can be picky, but nitrate makes it dissolve. Now you crisscross. So now you have sodium nitrate. Sodium nitrate, soluble or insoluble?
Soluble.
Soluble. Sodium, group 1A, soluble. Nitrate, always soluble. After that comes what? Ag3PO4. Soluble or insoluble? Insoluble. Phosphate, like think like phosphate, kind of like the feeling phosphate kind of gives. It just feels like it's like a rock or something. It won't dissolve. So anyway, so that's what it is. Okay. So phosphates, and what are the other ones? Phosphate, hydroxides also, and carbonates. These guys don't dissolve. The rest of them, most of them dissolve, and then there are some exceptions. Okay, so you get this now. Now, this guy, do not ionize this one. Do not ionize. Okay, the rest of them you will. So let's put this here. So you have 3 sodium ions plus 1 charge aqueous plus 1 phosphate ion minus 3 charge aqueous plus 3 silver ions plus 1 charge aqueous plus 3 nitrate ions minus 1 charge aqueous gives you 1 nitrate ion, 1 sodium ion plus 1 charge aqueous plus NO3 minus 1 charge aqueous plus Ag3PO4. Ag3PO4, and this is a solid. So do not ionize that. Okay? Everyone got the total ionic? It will come with practice also. Got it, everyone? So basically, you're just putting the charges and you already balanced it. You have that's all you need to do. Now, which ones are changing the state and which ones are not? Spectator ions are those. Spectator ions are those that are just onlookers, just watching. So there are 3 sodium ions, aqueous, and there are 3 nitrate ions. Oh, did we? I think I didn't put the number here. 3. This was 3 and this is 3. So this would be 3 sodium and this is 3 nitrate. Okay. So 3 NO3 minus 1 aqueous. Okay. Now, spectator ions. So what you get now, these guys, because they are, if you look at it, they are the sodium here, 3 sodiums here, aqueous, 3 nitrates aqueous here, and 3 nitrates aqueous here. So it's kind of like, we don't know in a test tube whether they are coming from the reactants or the product side. Then comes the net ionic equation. Net ionic is, which one? 3 silver ions plus 1 charge plus 3 plus 1 phosphate ion, PO4 minus 3 charge. This one is aqueous here, this one is aqueous here, but when it goes this side, it becomes Ag3PO4 and solid. That is the net ionic equation. Okay, guys? I mean, there's going to be no end to the review. You can spend a entire night on the review, but we have to like wrap up. And this is the last question from the. So, but I'm available tomorrow from 12 to 1. That's our lunchtime, even if you're working, and I'm pretty sure everyone is available at that time. So you guys, I'm available for one-on-one. You can come in the Zoom meeting. Okay, so anyway, so this is a test question, test 3. So you are given zinc as a solid. This is reacting with 2 moles of HCl. 2 moles of HCl as an aqueous, and this gives you H2 as a gas and zinc chloride, which is soluble in water, aqueous. Okay. All right. When 25 grams of zinc. So the question is saying, so write down 25.0 grams of zinc reacts. How many liters of hydrogen gas? So you need to find the volume of the hydrogen gas in liters. Of hydrogen gas is formed at the temperature given is 25 degrees Celsius and the pressure given is 854 millimeters of mercury. Okay, so these things are given. So important thing here is, since we are looking at a relationship of zinc to hydrogen, right? And it's all balanced. So one thing is that in this case, clearly, you know, whenever the temperature and pressure of this, well, that means that some gas law is going to be applied, but it's a mixed, like it's a stoichiometry and gas laws mixed type of problem. So in this case, first always convert the grams of the reactant to the moles of the reactant. Okay, that's one thing. Next is, from the stoichiometry, you're going to take the moles of the reactant and convert that to the moles of the product. Now here, do not, some of you have converted back to the grams and so forth. Stop. Why do we need that moles? We need the moles of the product because we need to put this in this problem. PV is equal to nRT. We have the value of pressure. We have the value of temperature. We know the value of R. We got the moles. This is equal to N. That is that we got the moles. We need to find the volume. So when you rearrange, volume in liters is equal to nRT over P. Okay, so let's do this. Grams of zinc. Grams of zinc is 25.0 grams of zinc times 1 mole of zinc is equal to, how many grams is that? 65 grams. Okay, and this gives you 0.3846 moles. Okay, so that's one first step. Next step is you take the moles of zinc and convert this to the moles of hydrogen because we need to find for hydrogen. So 0.3846 moles of zinc times it's 1 mole of hydrogen is produced when 1 mole of zinc is reacting. So this is the same 0.3846 moles of hydrogen. Okay, now the third step is we need to find the volume of hydrogen, and that is equal to nRT over P. Now, important thing here is either you can use the value of R as 62.4 or you can do the conversion. So let's do the conversion. You can do either way. R, you can use 62.4 liters times millimeters of mercury per mole K. Okay, because the pressure given is in, let's do this one first, 854 millimeters of mercury. Let's just do this one. Okay, so here you have volume of hydrogen is equal to 0.3846 times 62.4 liters times millimeters of mercury per mole K times the temperature. Okay, we've got to convert that to Kelvin. So 25 plus 273 is what? How much? 298 K. Okay, so that's the value you are going to put. 298 K over the pressure given is 854 millimeters of mercury. You can use that, or you can take 854 or 854 millimeters of mercury times 1 atm over 760 millimeters of mercury. So this gives you the pressure of, do it. I calculate that 854 divided by 760. Yes. 1.12, okay. 1.12 atm. So in this case, the value of R is, so let me write this down in red. So in this case, the value of R is 0.08206 liter atmosphere per mole K, because the pressure is 1.12 atm. Okay, so here you are just going to put the same formula. Volume of the hydrogen is equal to 0.3846. That's the moles times 0.08206 liters times atmosphere per mole K times, what is the other one? 1.12 atm over pressure, no, 1.12 atm. Okay, either you convert to so that just make sure that the pressure and R values match. Either way, it's fine. So this is going to give you 8.32 liters, and this should also give you 8.32 liters or closer, you know, a little bit here and there, but still it should be in that range. Okay.
That's on the last line you made a mistake.
What?
RT multiplied by the ATM.
Oh, this should be the temperature. Yeah, that's the temperature. Thank you. So 298. Okay, yeah. Thank you. All right. Okay, guys. Anything else? So keep this in mind here that you are going to look at the review sheet, because you know you can only cover very important pieces in a review session like that. But I have the review sheet also uploaded in the Canvas. So make sure that you look at the review sheet, go back and look at all your notes, your own notes. So some of you have really taken very good class notes. So excellent job on that. So all your notes and my lecture notes. Okay, so there are certain things you may have missed. So check my lecture notes, double check, especially double check if I'm writing anything in red. And then you can look at some of the homework questions, and you know, you already have the solutions manual. So you have the work solutions manual. Okay, guys, here's another question a student was asking. She spent only 2 hours and she thought that prepared for the chemistry exam. No. There are how many chapters? So, you know, chapter 1 is a very small chapter. Like what? Just maybe 10 minutes, 15 minutes. That's gonna be, because in the chapter 1, there is only, you know, that standard notation, scientific notation. So that's important. Chapter 2, I'm not giving anything very specific, you know, because there's already so much. So chapter 2 is also not very important. Then comes chapter 2, then comes chapter 3 is okay, but chapter 5, obviously we are not doing. So you can, like chapter 5 is definitely not coming. Chapter 5 is the nuclear chemistry. Nuclear chemistry, we're skipping that one for the exam. But chapter 2, so just, you know, just casually look at it, but don't spend too much time on it. Maybe half an hour if you want to, less than half an hour. So casually look at it. Okay, but the rest of them are important. So you have now from chapter 3, 4, 5, 6, 7, 8, 9, 10, and 11. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 chapters. Even if you do the review on every 9 chapters, 9 chapters, right? 2 hours. Remember, I already told you, you need 2 hours for chemistry every day. 2 hours. So that gives you how many hours you need to spend to prepare for the final? 18 hours. Now, I'm not saying do it in one day, obviously. Spread it out. Let the whole thing sink in your brain. And how many days are left from today for the exam? 1 week, but let's see exact date. Let's count the exact countdown. Yes. So, I mean, obviously, okay. So, 1 second. So, your test is on the 25th. So, 1, 2, 3. 1, 2, 3, 4, 5, 6. 6 days are left. 6 days. So roughly you need to spend at least 3 hours. And that 3 hours, you can give 3 hours, like 1.5 in the morning, 1.5 before going to bed. Manageable, right? But look at also the other. I also have another review sheet in which I have explained other things in more detail. So look at another review. Review. Review, what is that? Watch the video and then the review notes. They're all up on the board. Okay, guys? You can do it. All right. Thank you for being patient, and I'm just